All right, guys, so. For the warm up, what I'm gonna want you to do. What's today's date? The 30th, right? Please put your name. And then put the date. Put your first and last name, please. Or if you just want to put your last initial, that's fine, but I need to know, some people have the same name, same first name. Okay, so what I would like you to do is I would like you to go to Desmos.com, or it's on our Canvas page to help you graph the functions. I'm about to show you what they are. Once you graph them, try to review important properties of the graph. Maybe remind yourself of a couple of things. And then please write this down on your warm.
Mr. Wright warm up 1:30 and also the date, or?
I want you to write warm up, 1:30, the name and the date, correct?
Okay.
All of it. I need to know you were here and that it's you.
Oh, wait. Never mind, sorry. Oh, wait. Was it January 30th too?
Today is the 30th, right?
Yeah.
Yeah.
Yeah. today's
Okay.
30th.
So that's also the date,
The dates.
written twice,
Did I write it twice?
or just. Maybe, I'm sorry.
Here, it's okay. Warm up, it should say warm up, not warm. And then put the date. Yeah. It's our first time, so. So it's all good, don't worry. Okay, so here's the way I want you guys to graph. So I want you to do a linear function. And I want you to graph right below that this function, y equals x minus 2. And then put the graph right here, right below it. And then we have a quadratic function. Do y equals x squared, and then do the graph right below it.
You just be like a 3 points graph and,
I want the curve of the graph.
yeah.
Yeah, maybe plot a couple points if you want. So we go to, go back. Right here. Desmos graphing calculator. Yeah, there it is. Or if you have a graphing calculator, that's fine too. Okay.
That's my notification.
Oh, okay, okay. Let's see. Wait, just the camera, will you guys doing that? Yeah, perfect. Now, I don't really want you guys spending too much time plotting points. That's why I want you guys to use a graphing calculator. Because then that's gonna take too long. We're gonna spend a whole day reviewing linear functions, and we're gonna spend another whole day reviewing quadratics, okay? Right now, I just kind of want you guys to see, remind yourself what the graphs look like. Feel for it. Sorry, it looks like some of the little small sheets went blank on one side. I apologize. So usually the warm-ups are pretty chill, they're not too intense. Like in that mood. I also just want you guys to like know how to find that. Yeah. Walking around, starting to learn some names here. Yeah. Okay. Okay, if you can, just real quick, just check your neighbor's graphs, make sure they're matching to your graph. The location of where it's at, the way it's facing, the way it's shooting towards, the ends, or they usually call them the tails of the graphs. Just a quick little review on that. Oh, yeah. Warmer down. All righty. Let's see. So I'm gonna do it with you guys. Just to do a quick little review on that. Let's see. Whoops. Let me open a completely different window. Hold on. Okay, let's see. So you got y equals x minus 2. So remember this form right here in the linear equation, the famous mx plus b, called the slope-intercept form. We're going to spend more time on that in another day. But remember that the numerical value that's in front of the x is what we're calling the slope. Okay, we're going to talk about that a little bit later. In this case, what's the slope of this linear equation? 1, because that's the numerical, that's the coefficient of x, right? How can you write 1 as a fraction? 1 over 1. So then in this case, the slope is 1 over 1. B, what does the b value tell you? Not quite, it's where it's positioned. So it's it's called the y-intercept, the point where it crosses the y-axis. So it's -2, so it crosses at -2. If I had -3, then it crosses at -3. Okay, so that value there, it's called a constant because there's no x multiplying it. That constant value b is where it crosses the y-axis. So I did see some people having the line crossing at the origin. That would be if there was no constant value like that, because in that case, b would be 0. Okay, so the way you normally graph linear equations, you start at the b value, -2, and then the slope is your guide. It tells you how to increase in the line. So because the slope is 1 over 1, that means that starting at this point, you're going to go, what does the slope tell you to do? Positive. So you're going to go up 1 unit, over 1 unit in the x direction. And then you just keep doing that. Up 1, over 1, up 1, over 1. And so notice that gives you this line right here with all these points. If the slope was 1/2, then you would increase y by 1, and x would increase by 2 units, and it'd go like that. We're going to spend more time on that later on, okay? But that's a quick review. Okay, so then you should get this linear equation here. And then let's see. So that should look something like this. 1, 2. So then your line goes, you start at y is -2, and you go up 1, over 1, up 1, over 1, and you just keep doing that. Something that's very important, guys, is I want you guys to practice reading graphs from left to right. That's very important, okay? Left to right, so from left to right. So then that gives you a line, oops. Like that. Then we have our second equation, which is x squared. That one gives you a parabola. The origin is, or sorry, what's this point here at the bottom of the parabola called? Well, that's the point that's the point 0, 0. But in general, that bottommost point of the parabola starts with a V. It's called the vertex. In this case, the vertex is the origin. So it starts here. And parabolically going up this way, we're going to talk more about that later. But if you plugged in some points and you plug in -1 or +1, when you square those, the y value will be 1. Like that. Okay. We'll spend more time on quadratic equations, but in general, I just kind of wanted you to remember the shape of these graphs. The parabola will go like that. Opening up. Okay. Something simple, nothing crazy. Pass up your warm-ups. Pass them up. Thank you. That's okay. Okay, let me look today. Yeah, I'll wait. I promise next time I'll get more small. It's easier to collect them. All right. Thank you. You know. Let me put these in the back. Harder to. All right. Okay, guys, so we're gonna start with piecewise functions, which is covered in section 3.2. The section 3.2 piecewise functions. The heck is that? If you've never seen it. So what exactly is a piecewise function? So a piecewise function is, you think of it as a function that's composed of a bunch of different functions, but at different time intervals. And I'll show you what I mean by that. So think of it as a function composed of different functions at different time intervals. And I'll show you what I mean by that. Different. Now here, time, I think I'm using time just because it's makes it a little bit more tangible to think of it as the input values being time. And I'll show you what I mean. And so let's look at an example. Normally piecewise functions, you write them with a big old bracket, a big set bracket like this, but it's a really big one. On the top, you put your first function, and on the bottom, you put your second, and sometimes there's a third function, fourth, whatever. In this case, we're just going to do 2. So we're going to use this function from the warm-up, x minus 2. But we're only going to consider this function for the x values if those x values are less than or equal to 1. And I'll show you what that means. So if it's greater than 1, then we're going to consider this function, x squared. So I'm going to write that down here, x squared. I'm going to say if x is greater than 1. And so what I'm kind of, what I'm doing is I'm making a function that behaves like the linear function, but only for x intervals 1 or smaller. And then I want it to behave like the quadratic function for x values that are greater than 1. Okay? Now, if I think of the intervals for this, think of the x-axis. How would I write x values less than or equal to 1 in interval notation? Can I have you guys do that super quickly just to review that? How would you write these values in interval notation? Remember, parentheses or square bracket, do I include an infinity? Do I not include infinity? So how would you write these in interval notation, these x values? Let me have you guys do that super quick. Interval notation. Looking good. All right. What's the biggest x value that you can get to? 1. Can you include it?
Yes.
Yes. What's the smallest x value? That's right. There is no, so you put negative infinity. So that's that interval. We're considering that interval in a domain here. We're using this function here. This guy is, what's the smallest x value you can get to? 1, but you can't include it. And then everything greater. So it would look something like that. An interval notation. Okay. Why is that important? Because on the homework, they're going to give you a piecewise function composed of 2 functions for different intervals. And they would say, let's say, let's call these 2 different problems. Say you plug in 0 into this function. Actually, we do it. When you plug in 0, think of it kind of like a little machine. You plug in 0 here, and you have to decide, do I plug that 0 into this first function or to this second function? And this is kind of the condition of that x value. So you have to ask yourself, well, is the x value less than or equal to 1, or is it greater than 1? It's less than or equal to 1, right? So you look at that x value you're plugging in, and you say, because 0 is less than or equal to 1, you're going to use the function x minus 2, the first one. It satisfies this condition, so I use this guy. That means you're going to plug in 0 in here and ignore the bottom. You just plug it in like that. All right? So what's 0 minus 2? Negative 2. Let's say instead, they have you plug in the x value 5 in this case. So before you plug it in, you check the condition. Does it satisfy the top condition or the bottom condition? Bottom. So because 5 is greater than 1, you're going to use the x squared function. So then you plug that 5 into this function and ignore the top. So you plug in the 5, you square it, and you get 25. Okay? You can't plug it into both, because if I did that, I would get 25. And then what would happen if I plug the 5 minus 2 here? What number would I get? 3. But remember, a function can't have an input give you two different values. It can only do one. So this is the condition that tells you which one to choose. Okay? Not too crazy? Question, yeah.
So if we got the number 8, for example, we would have to do x squared because it's 8 squared.
Exactly. Yep.
And if it was negative 3, obviously it was x times changeable.
Yeah.
Okay.
What if you plugged in the x value 1?
You have to do the top one. Because it's equal to-
Because it could be equal to 1, right? Yeah. So you gotta be careful with that kind of like that breaking point.
So we're just solving for what has to make sense.
Exactly. You see which condition is satisfied, and then you use that function. And then that is the output value. Okay? The harder part of piecewise functions is graphing them, seeing how they're graphing them. And that's why I had you do this. Okay, so you can quickly remember what those graphs look like. So for number 3, let's say you're being asked to graph f. And so here's the strategy that you're going to be using. You're going to want to graph both functions, but only on the intervals that satisfy those conditions. So for example, you're going to graph y equals x minus 2 for the interval -infinity to 1. And you want to make sure you include the 1 because there's an equal here. And then you're going to graph the second function, which is x squared, but you're only going to do it for the second interval, 1 to infinity. So you're going to do it one at a time. See, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 4, -1, -2, -3, 4. So what do I mean by that? See how this guy right here? This is the graph of x minus 2. But this, you graphed it for all x values. So I'm going to graph that whole line again, right? Starts at -2. The slope is 1 over 1. So I'm going to do the same thing. I'm going to graph this guy, but only for x values up to 1, and then including 1. Okay? So that means it's at -2. The slope goes up 1 over 1. But I can't keep going. It has to be for x values 1 less than or equal to 1. So then only this part of the line is drawn. Only that part of the line is drawn. I can't draw, I mean, I guess you can think of it as like dotted or something, the rest of the line, but you don't draw the rest of the line because you're only doing it for x values up to 1. Okay. Now, do you guys see how there's a square bracket because it could equal 1? So this square bracket tells you that your point is filled. What the hell do I mean by that? It's included, meaning you don't do this. You need to include that point at that x value. So that needs to be filled. That point is completely included. Okay? Questions on that part of the line? What if this said x less than or equal to -1? How does the graph change? Does the shape of the graph change at all? No, it's just at -1 and below. Then you would erase that part over here. Okay. So yeah, so it's up to 1 in this case. So then you graph the second equation, which is the parabola that you guys did here, but only for x values greater than 1. What does that look like? Well, we know the parabola from what you guys did. We know the parabola is going to look something like this, right? That's like the shape of the parabola. But you need to start drawing it at 1 and greater. But you guys see how you're not including the 1? So what do you think you're going to do? You're going to do an open circle. Let me write what you guys said. But usually your textbook will say it's a hole on the graph. So when you plug in 1 into this function, what's the y value that you got? Let me say it over here. When you guys plugged in 1, what was the y value? It was also 1, right? So then you're going to start your parabola at that point. When you plug in 1, you get 1, but it has to be an open circle there. And then you draw the rest of the parabola for x values greater than 1. and the rest of the parabola is completely ignored. I know. Questions? Yeah, time for questions.
So if it was like, so if it was -1 for that first problem, how would you do it since there'd be no y-intercept, since it would never hit 2? Because it wouldn't hit the.
Oh, like if you had the -1 here,
Yeah,
then you would have done, I mean, the way I like to do it is I kind of like to do it the way I did in the warm-up, is draw the whole graph. And then just erase the part that I don't want. So I would draw the whole line. And then that -1, I know it's a solid point. And then I would just erase all that, like that. Then that would be it. If this was the piecewise function with a -1, like that. Yeah. Go back. Okay. Questions? Maybe a question you think someone else might have?
Just for like on exam, you want us to dot the rest of the graph because we didn't do it.
You could. It wouldn't be wrong if you did. Just so I can see that you were like getting the overall shape of it. Yeah. But I would definitely make sure that your points that are open and closed would be in the right spots.
So if the bottom blue line was a parabola, that would be a function because one equivalence of the next.
Say that one more time.
If the blue one was a parabola, then this would be a function because one's closed and one's open.
As long, it would. Not quite. It could still be another parabola. The blue one could be another parabola.
Okay.
You just can't have, remember we talked about the vertical line test? You just can't have a vertical line cross the graph. These two pieces, guys, are not two different graphs. They're one graph of the piecewise function. It's just a disconnected graph. Yeah, but technically, you know what? Let me put it blue so that you don't think it's a completely different graph. It's like, this is the graph of f of this piecewise function. And if I cross it with a vertical line, in this case, it does not cross it more than once. Yeah, more than once. Yeah, but the bottom graph could be whatever other function it is. It just has to pass the vertical line test for it to be a function.
And then for these piecewise things, is one gonna be linear and one's gonna be a parabola?
Not always,
Okay.
not always. Yeah, I think the homework will like make one be an absolute value function. One of them will be like a square root function. So you can use Desmos to kind of help you review what those graphs look like. Yeah. At the back of your textbook, there's also like a guide to help you remember what the graphs of different functions look like. Okay. Okay, so we're gonna spend some time here. I'm gonna give you guys a worksheet that you're gonna work with your classmates. I giving you a piecewise function. So for the front part of the worksheet, you're gonna do this, what we did for problems 1 and 2. Is that. For the back part of the worksheet, you're gonna get a different piecewise function, and then I'm gonna want you to graph it. Okay? You're super encouraged to work with your classmates. I'm just do like the linking thing and no, but COVID like I got all it. Actually talking about that. Huh? Actually it helps. Are you working on this? It's a good time to ask questions. Oh, hold on, before I forget. Anytime we do a worksheet in class, there will be solutions posted. If you look at the Canvas modules where the videos are posted, that page is called videos and handouts. That's where I'm going to post the solutions to these worksheets. You do not have to submit the worksheets. They're for you to keep to help you with the homework, because the homework problems will look similar to the worksheet problem.
Do you have like a online version of the worksheet?
I'm not gonna post the online versions only because I'm recording the class and I'm posting like, I kind of need you to come to class. This is not an online class. Okay, printed 42, so I should have enough. I'm just gonna give you guys a little stack. Some grabbers have to down. Question. Anyone have a question? No? Okay. All right, guys, so let me have you guys work on these for a little bit. And they also kind of have a little bit of instruction of what we talked about. So let's see. You four here work together. We have you four here work together. Okay, you four here. I'll just have you check in with that. Who needs a worksheet? I have extras. Okay. Let's see, I'm gonna have you four here work together. You four here. Can I have you four here work together, check in with one another? Are you guys here? You four work with each other. Together. I'll have you three here. Checking with each other. You three here, checking with each other. And then you four here. For to show some of your work, you can please, I can walk around and kind of see it. Sounds like a really loud mosquito. Have you seen one before and you're comfortable, please help your classmates. I'll walk around, just put your hand up and I'll come help you guys out. For the one. Yeah.
For C, are you guys doing it in the two, I just did
Hold on, guys, the format of the worksheet is a little funky.
I don't know.
Let me double check something. Hold on. Yeah. Oh, crap. Hold on. Determine which function. Oh, yeah, what the hell? Hold on, give me 1 second. Determine which function of the piece one. Okay, it looks like the worksheet misplaced some of the stuff. Just do for both for all three of those piecewise functions, do -3, and let's just do f of 0 for all three of those piecewise functions.
Aren't they the same? I think that was.
They're all the same, and there's 3 as well.
What do I do here? I converted it, like, it was a PDF and I converted it to Word. Fucking Word, brother. Let me see.
It looks like ours do all the same.
Okay,
Yeah, it's.
yeah, so for the same piecewise function.
Camera.
Oh, no, the camera fell. Let me pause the recording. I'll fix it. You can leave it there. Hold on.
Yeah, I got this video.
Very careful when you draw your open.
Yeah.
Andrew, you have
There's a.
It's not an equal song. Less.
It's the same as X.
You can grab those. You know
Biology.
I'm just talking about the concept of.
I have to take back once because I didn't do weird. I want to save more money. Just like when I-
Yeah.
Yeah. It's been a great. Like you're gonna see when it's like ringing on.
That's what. No, I guess I was just saying like. this could be- like,
I was going
Look, something we could be. You never seen that one? It's like, this one.
Yeah, definitely.
Guys, you can use Desmos to help you with the graphs, okay? You can use Desmos to help.
Yeah, I forgot there was a backside.
That's why, yeah.
And then check with your classmates, so your group mates there help each other out. Help each other out.
It's basically. Like using both, so like -2. You have the first one.
Or they can.
For X squared.
You're
So,
not.
X squared.
You're finished, check with your group mates. Help them. For the back, it's a completely different problem. There's no the front side.
That's the other side.
Oh, it's too late. You just, yeah.
That would be a. And where would the dot a? You wanna use ours. Maybe like.
It's pretty good. You're taking into account is what this says, is the endpoint. is
Yeah.
If the endpoint is not included, please conform with that. If the graph is not. It's all positive. What I meant by that is, you see right here, the X value -2 is included, but on this one, it is not included. We think that would work. I think that would be the best. Perfect. Thank you. That's it.
Wait, you mean like? Yeah. Like, that's just like, so getting those, they're like, getting the word less than 0. Like here, like we could go. But on the other side. And
All right, guys, real quick on the back. Oh, let me make sure it's recording. Yes, recording. Okay, real quick. So let's see, on the back side, there's actually, let me go on this side. So you guys have x squared. If x is in between -2 and 2. And then absolute value of x is greater than or equal to 2. Yeah. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So we said this is just your parabola, right? And so this, now that you're kind of actually trying to do it yourself, that's why I was saying I myself like to do kind of like a sketch of what the graph will look like. Okay. But then we got to take into account the bounds of this, right? So the bounds are at -2 and +2. And what I was trying to say in the worksheet is you plug in those bounds into the function. But if it doesn't equal the 2, you're going to have an open circle at that point. And if it does equal it, then you have a closed circle at that point. So when you plug in 2, you're going to plug it into the first function. So what's 2 squared? 4. So that means you have a point at 2, 4. Open or closed? Open, because it does not equal the 2. What about when you plug in x equals -2 and you square it? Also 4, but in this case, it is closed. That should be more right here. And then everything in between -2 and 2. So then everything in between these x values, -2 and 2, you include that part of the parabola, and then you ignore the rest of the parabola. Okay? Then you got your absolute value function. Again, you can use the Desmos for now, but absolute value function, whatever x value you plug in, you get positive y value of that. So that looks like this kind of at 2, 2, 3, 3, 4, 4, 5, 5, and so on. It has this like V shape to it. -2, +2, and then -3, 3. So the absolute value has this shape that looks like this, like a V. Okay. But you're only going to graph it from 2 on, right? So from 2 on, I do a closed circle because it equals there at 2. And then I draw the rest of the V shape, and then I ignore the other part of the absolute value graph. So it hopefully looks something like that.
Where did that, why is it at 2, 2?
At 2, 2, because when you plug in the 2 here, the absolute value of 2 is 2. versus here, it was squared. Yeah, question.
So when you do it for square, it's like you're plugging in and now it is y equals x squared.
Correct. Yeah, exactly. Yeah, because I think I saw some people put the points right on top of each other. And by the shape of the two graphs, they won't land on top of each other. Sometimes they do, sometimes they won't. Question.
And so you're not supposed to just connect these lines. And stop it, because at first I kind of had like a hook and then I stopped it and then I go to the.
Yep. No, yeah. It's in that most of the time, piecewise functions are disconnected. It's rare when they're really connected like that.
When they are connected like that, how would you draw that?
If they end up being connected, like if this graph ended up being on top of itself like that, then that you would just put it on top of itself. And sometimes this forces it to be an open hole, but the other guy says, what I need to fill it, and it also lands right on top of it. So that's fine. Yeah.
To be a function, does it need to be continuous?
Does not. Yeah. You'll talk about that in calculus, actually, more about what that means. So for now, that's why I want to present this, because I need you guys to be comfortable with very weird detached graphs. Okay. The reason I think of these as time intervals is because normally a piecewise function, when you use it in the real world, most of the time it has to do with time. So you're using a function to model something, and then from maybe time here can't be negative, but from a certain time interval, that whatever you're modeling behaves like a parabola, but then after that time where that makes a jump, then it behaves in a completely different way, right? You're driving a car and you're using a function to model how it's moving, and then boom, you get in a car accident, and now the car's motion is completely different immediately. So that would be a completely different function modeling that. Okay. All right, let's take a break. Come back at 1:50, and then we're going to start our rates of change. Good job, guys. So let's resume at 1:50. And while you do that, I'm going to fix the format of that worksheet, because that was fucking all bad. All right, if you guys could put those worksheets away, we are done with piecewise functions. We're going to start rates of change. All right, I like this section. All right, section 3.3, rates of change. If you end up having to take a physics class, this is very applicable to that class. Econ, also very applicable. Calculus. Say it again? Calculus, hell of applicable. Like ultra, it's the core actually. But this section specifically. Have you heard of the word derivatives? Yeah. This is what you need to know to understand a derivative. Okay? Maybe at the end of class, I think you'll be able to, we'll maybe do a quick discussion on what that would be, but we don't have to. Okay. All right, guys. So let's do a quick review. Quick review of slopes. So draw a little XY coordinate plane here. And we're going to have our X values A and our X values B here. And let's say we have 2 points. Let's say one's right here and the other point is right here at those X values, okay? And so there's a line that's going to go through those 2 points. When you plug in the X value A, oh, here, let me do this. So there's a line that goes through these 2 points. And that line is given by some linear equation. Let's call it f of x. Okay, easy. There we go. So when you plug in A to get that point, you're really plugging that A into f. Cool. So that y value, what are we going to call it? Now f of x f of a, yeah, f of a, close, yeah. And that has this y value, so that's the coordinates of this point are the x value we're calling a, but the y value we're calling f of a. And then for the second point, same story. This point is above the x value b. What's the y value gonna be called? F of b. So then the coordinates of this point are the x value b and the y value f of b that it corresponds to. And so when you guys are learning slopes, you're talking about lines and you're talking about how they're inclined. The rate at which they're being inclined. And so that's where you guys learned something called rise over run. As you go from left to right. The rise is if I pick a point on the lines and I pick another point on the line, how much did you rise? How much did you change the y values by? So that's what we're going to call the rise. And then the run is how much do the x values change? So what was that horizontal change to go from this point to this point? That's what we're calling the run. And so in your past math classes, you guys covered the slope. Usually you use the letter M for it to be rise over run. But we're going to get a little bit more sophisticated than rise over run. And the rise, what things do you have to do with A, B, or f of A and f of B to figure out that change in distance here? What would you do to figure that out?
-1 over x2 minus x1.
Okay, yep. And let's see, why was that? Because if I subtract these two y values, that'll be the distance between those y values, which is the rise. And when you subtract the x value, that's the change from this x value to this x value. Question.
So that's the same as delta y with delta x.
Exactly. And so in this textbook, this right here is written like this. It's called delta y. When you guys see a delta, that means the change in the y coordinates over the change in the x coordinates. Okay. This is the change in y. And then down here is the change in x. But they're not going to use this notation that you guys learned in your past algebra class. Because now the y values are thought of as outputs of functions. So what are we calling that second y value? We're calling it f of b. The second y value here is talking about the y value f of b minus the first y value, which what are we calling that? F of a. What's the second x value? B minus the first x value, which we're calling a. Okay. And so obviously, this is an important concept in a math class because there's hella different ways of saying the same thing. Okay, because they have a lot of applications. Whenever you figure out the slope, you get a number, right? Whatever that number is, but that number is a numerical representation of the slant of this line. Okay, so this numerical value, whatever you end up getting, tells us the rate of how the line crossing those 2 points, the line is increasing or it could be decreasing. If you do this here, you compute this, the slope, and you get a positive answer, that means that your y values are going to be increasing as x increases. But if you get a negative answer, that means the y values are decreasing as x increases. Okay? So right below this, let's do an example. That way you kind of put all this together here.
Wait,
So the-
so just the number at the bottom is gonna tell us the derivative?
Oh, no. When I do this, I'm in the whole thing.
Okay.
Yeah, I'm in the whole thing. Sorry. Good. Right, let's take you back to your past algebra class real quick. So you have a point, 1, 2. Oh shit, that's all that. Hold on. Let me just make it up 2, like that. So let's say this is the point 2, 3, and this is the point 6, 4. There's a line crossing those 2 points. And you're asked to find the slope of the line. Let's do it a little bit. Wait for a little bit. All right. So the change in y over the change in x. So what are the two x values that we're talking about here?
6 and 4.
6 and 4. 6 and 4?
No, 6 and 2.
6 and 2. 6 and 2. And what are the two y values that we're talking about?
3 and 4, 3 and 1.
3, the y value 3. Oh, this is hella off, but whatever. 3 and 4.
Oh, I thought I was going crazy.
I know the increments are like. But let's see. So according to what I need to do is I need to find the change in the y's and the x's. So I'm going to do notation. So I'm going to subtract the second x value minus the first x value. So that's 6 minus 2. That's like the b minus a. And then I'm going to subtract the output value of 6, which is in this case 4, but I'm just gonna start with you guys mirror the notation, minus f of what? F of 2, which ends up being, what's f of 6? What's the output value of 6?
4,
The y value 4. What's the output value of 2?
3.
It ends up being the y value 3. And then on the bottom, we got that. So then I just go ahead and subtract. What's 4 minus 3? 1 over 4. How would I write this as a decimal? 0.25. I can think of 0.25 over 1 because slopes, I want to write them as fractions. Okay. Okay. That's the way you numerically do it. But now the important part is the interpretation of what's happening. Because the line has slope 1/4 or slope 0.25, what does this tell me about how the line is changed? The points on the line are changed. For every increase of each, y will increase 1 unit every time x increases 4 units. Okay, or what does this tell me? Y, exactly, y will increase 0.25 units every time x increases by 1 unit. So there are two rates that really tell the same story, but in a different way. Okay. Okay. So that's the quick review of slope. Okay. So you guys learned this, but now we're going to talk about rates of change and leave this in the background because it'll tie in a little bit. All right. So back in the 1500s, there was an astronomer named Galileo, wanted to study the motion of things, right? So one experiment that he was doing was dropping, I think the story says dropping pebbles, but I'm not sure what he was dropping, but let's say he was dropping pebbles and he was gathering data to see, how long did how long did the pebble fall after a certain amount of time? So let's talk about that real quick. So back in the 1500s, we have astronomer Galileo discovered that for a still object, that suddenly free falls, the distance y in meters, the distance, let's put comma, y in meters, it travels. Does travel have one L or two L's? One. It travels after X seconds, has the relation y equals 4.9 x squared. Okay. And so through a bunch of the data that he was gathering, he discovered that there was a relationship between how the rock was falling and the time that the rock was falling. And so let's say we have a little picture. So we have a little picture here. This is right now the rock has not fallen at all. So right now the distance that the rock has traveled is 0 meters. Okay. Let's say this is at 0 seconds. That's you. Then, actually, put that. We're going to draw a little picture here. Let's make a little XY table here. Put 0, 1, 2, and let's just go up to 3. So this is seconds. This is meters. So yes, if the rock has not even fallen, then it has traveled 0 meters. But after 1 second, you plug in the 1 in for X, and what's the Y value that you get? 4.9 meters. So that means that after 1 second, let's say this is 4.9 meters. This is at 1 second. Help me out here. Then at 2 seconds, now it has traveled a total distance of, well, you're going to plug in 2 and then square it.
19.6.
That's 4 times 4.9, which is 19.6. So then now from 0 to 2 seconds, it has traveled a total of 19.6 seconds, meters, sorry. In 2 seconds, correct. So in 2 seconds, it traveled that much. And then in 3 seconds, plug the 3 in here, 44.1. So then from 0 to 3 seconds, the pebble has fallen 44.1 meters after 3 seconds, in 3 seconds, correct. Okay, that was the relationship that he found. So what we're going to do is we're going to talk about, right now we're going to ignore this for a bit, but what we're going to discuss is what's called the average rate of change. So from 1 second, we're going to play around with from 1 second to 3 seconds on average, how is it changing? How much distance did it fall on average? Okay. Let's see. So this room. Okay. So to find the average rate of change And if this was a physics class, it's called the average velocity. Because we're talking about motion here. So to find the average rate of change or the average velocity that the object travels, you guys said it's 1L, right? I don't know why I'm tripping. Okay, travels from x equaling 1 second to x equaling 3 seconds. We compute the change in the distance that it traveled over the change in the time that it traveled. Okay, within the span of time here. What is the coordinate we're using to represent distance? We're using y. So that means that we're doing the change in the y units. And what's the one that's representing time? It's the change over x. Now, to find this specific one here, what time are we considering that we're starting? What time are we starting? How many seconds?
0.
Well, notice that saying from 1 second to 3 seconds, right? So it starts from 1 to 3 seconds. So how will we find the change in that time? What do we do to those two values? You subtract them. So you would do 3 minus 1, the time that you ended at minus the time that you started at. Okay? Now to find the distance though, you would need to know at 3 seconds, how far did the pebble travel?
44.1.
44.1 in this case. But we're thinking of this guy. We're going to think of it as a function now. Okay. So in general, at 3 seconds, how do I figure out that distance by using the function? What would I have to do to that 3? Plug it in. Exactly. So to find the distance at 3 seconds, you would find the total distance it traveled at 3 seconds minus the distance that you were at 1 second. Okay. We calculated that already. What is the distance at 3 seconds?
44.1.
44.1 minus, what's the distance at 1 second? 4.9. And then 3 minus 1 is 2. So let's see, I think I did that for you guys already. 39.2 over 2, which is 19.6. Now, because this is an application problem, it has units. We're using meters over seconds. So then that means that on average, the distance that the pebble or the object fell from 1 second to 3 seconds is an average of 19 meters per second. 19.6 meters per second. Okay. So notice that to find this average rate of change, it looks very similar to what we were doing when finding slope. Okay. So let me show you guys that that's not an accident. That looks like the slope of something. So let's see what it's the slope of. So let me see. I think I already have all this ready for you guys. Yeah. Okay. Let me get rid of all this crap. Okay. So if I plot that function, f of x equals 4.9x squared, that's a quadratic function, right? So the graph is a parabola. And the 4.9 stretches it a little bit. So that's why it's a little stretched. So then what I did is I used the function and I plugged in 1, gave me 4.9. I plugged in 3, gave me 44.1. So that's these points right there. the ones that you guys helped me find. Okay? If I asked you to find the slope of the line connecting those 2 points, you would do it the same way that we did it right here. You would do the change in the y coordinates over the change in the x coordinates. And it would literally give you the same computational answer as 19.6. So that means that the average rate of change that models this real world application, we're thinking of it as average velocity. In mathematical representation, it really represents the slope of this line. And this line, any line that crosses the graph at 2 different points is called a secant line. A secant line. So this average rate of change is exactly the slope of the secant line here. Okay? If instead the problem said, find the average rate of change from 1 second to 2 seconds, now that would be talking about the line crossing the points from 1 second to 2 seconds. Okay? And see how that one slanted in a different way? That one has a slope of 14.7. Okay, yeah, questions?
What X minus B up there? On the second one.
This,
Okay.
that, or
The blue one?
the blue one,
Yeah.
this thing, that's the equation of the line.
Oh.
Don't worry, you don't have to do that. You will in calculus, but right now you don't have to. Right now I'm just using it so it codes it. Okay. Okay. So that means that the slope, the average rate of change from 1 second to 2 seconds is really the slope of this secant line connecting it from 1 to 2, which is 14.7. And then what if I want to do the rate of change from 1 second to 1.5 seconds? So I would move it to 1.5. The average rate of change from 1 second to 1.5 seconds is 12.25 seconds. So on average, between 0.50 seconds, it's going to increase on average 12.25 units. So what you're going to do in calculus is you're going to study how this average rate of change behaves as you get closer to 1 second. So you know when you guys are driving your car and you look at the speedometer, that's giving you the average rate of change of your speed, right? It's giving you the speed, but not the average. It's giving you the what's called the instant speed. Like at that moment in time, how fast are you traveling? But when you find rate of change, you need 2 different points. But in this case, I just have 1 point because I'm looking at that moment in time. So what you end up what you're going to do when you guys start a calculus class is you're going to find this average rate of change, but you're going to see what happens as this point starts to get closer to the x value 1. And so it gets closer and closer and closer. And look, you guys see how this slope is approaching a particular value? It's getting closer and closer and closer to like about 10 point something. You're not going to do that in this class, but I'm just showing you what you're going to do. That's kind of the idea of what you're going to when you're going to do when you guys first start a calculus class. But right now, all you need to know how to do is how to compute an average rate of change at two different x values. Okay. All right. So what ends up being hard about this class and a calculus class is that you guys are going to have to do a lot of algebra and a lot of graphical work, and then interpret it, what it's really doing in the thing that you're modeling. And that's where it gets really tricky. Okay, because you'll get so lost in all that formulas and all the algebra, you're like, what the hell am I doing again? Because there's so much work. But you gotta keep going back and forth between those two things. So yes, so in this case, this gives you the average. Oops, I'm sorry, share my screen. That still gives you the average rate of change, but it also represents the slope of the secant line from x equals 1 to x equals 3 that we were looking at on this. Those two things are the same, they equal the same value. And so that was just this particular example that we were looking at to kind of motivate what's happening. And so in general, the average rate of change for any function f on the interval from x equaling a to x equaling b, like what we did right now, from 1 to 3. But this is in general, is given by finding out the change in the y coordinates over the change in the x coordinates, which in this case, you need to find the change of these two x coordinates. So you subtract them. And then you need to find the change of the y values. So you subtract their outputs, just the way we were doing it right now. And the graphical connection that that rate has is that your graph could look however you want it to look. It could be all kinds of weird curves. Okay, it could be a piecewise function. But if x is equaling a here, and let's say b over here, you plug in a into f, and then you get a point. You plug in b into f, and then you get another point. Right, this is the graph of f. And this rate of change that you get, just like this one, is going to equal the slope of the secant line connecting those 2 points, just the way this one. Okay, let me do this green. So this slope here of the secant line equals that average rate of change. Okay, that was a lot of me talking, sorry. It's not that bad. And my voice is a little like raspy. I went to a wrestling match last weekend. And I was like, hell sweet. So it's a little gone. Okay, so here I'm gonna have you guys try it out. I'm gonna have you guys do some of them and then interpret what your answers are going to be, okay? So what I would like you guys to do is compute the average rate of change for the function x squared on the given intervals. Once you find that, then I want you to discuss with your classmates what conclusions can you make about how the y values of the graph are changing. You already know the graph of x squared, but just use your interpretation of the answers to see if it agrees. So let's do part 1. Let's call this problem 1, problem 2, problem 3. So find the average rate of change from the interval x equals -2 to x equals 0. then do it for x equaling 0 to x equaling 1. And then from x equaling 1 to x equaling 3.
I have a question. The second one on this one is the blue one?
The second one,
No, on this one, the slope of second one.
it's the blue line. Yeah, sorry, let me do this. Let me do this. I know visually, I saw that too when I wrote it. Let me put this graph like that.
How come you use this type of notation, like -2 to 0 doesn't it include -1,
It does.
but you just want to find the rate of change from 0 to -2 or negative?
From
2 to
-2 to 0. Yeah,
So
yeah.
why you include -1?
Because that's the kind of the essence of average, is that you're looking at it from with a span of time. So like if I'm traveling somewhere, let's say I'm on a road trip, and I'm saying, on average, how fast was I going from the first hour that I was driving to the third hour that I was driving?
Mhm.
So you don't look at the hours in between, you just look at the starting hour that you want, and then the ending hour that you want. Yeah.
Okay.
Mhm. And so that's why the second question is kind of talking more about what you're asking. Question.
So, which one do you plug into the function?
So when you guys see this time interval here, think of it like this. So think of reading this as from x equaling -2 to x equaling 0. That's kind of what that's telling you. So then you would plug in these x values. And not the ones in between, only the ones from that span of time, the starting time to the ending time. Okay, go for it, guys. Let me have you try it. Work with the same people that I grouped you guys up with. So remember, to find the average rate, you're going to see the change in the y values over the change in the x values. And so you're going to use this to help you compute that.
Let's start. That's what I guess I think this. I don't know if this is the.
Okay.
And then this the x squared is so there's to
So are you plugging in 0 here?
yeah.
Okay, so when you plug in 0, you're plugging 0.
Yeah.
So what's 0 squared? 0. So then that should just be 0.
And then that's just and then 1.
You don't have to plug in 1. You know, that's what they were asking. you.
Just
It's just those endpoints.
okay.
Yeah.
I have a question. Okay, so I got here. Would I use plug in -2 into x?
Exactly.
Oh,
Mhm.
okay.
Yeah, if this function was different, then you would plug in 2 to the other different function.
Okay.
Yeah. I'm also purposely writing the questions the way WebAssembly will write it, in case you're like, confused by the question, then I can clarify it now.
Could I do the same thing? I can't do the same thing for the 0. Would it just turn into 1 for 0?
You would plug in the 0 here as well.
Yeah.
And then 0 squared means 0 is up to 0, which is just 0.
Yeah.
Mhm.
Okay.
Okay, so then try to see what is that code? Change it after.
This one, going back, so going from -2 to 0, so I got like, I'm that. Like this, something around more than that. This is the value of your book. So I mean, like, I'm just trying to explain why like this is what looks good. Like the rate of change that the first line. So I think the class one's there. The rate of traffic nearing.
Oh, you-
is what
That's how you get around.
I know that -2 is. If we're looking, I don't know what the guy is, I know the -2 point would be higher than. Correct. Yeah.
What about these two?
And they're both increasing because it's a positive rate.
And, okay, so they're both increasing, but which one increasing more?
So.
On average. It can still be going down a little bit, but on average, it'll tend to go up.
Thank you.
All right, guys, don't hide me right now. Just stop what you're doing, check in with each other. Your groups, you guys kind of seem to be in different places, so just check in with each other, do a quick, scan.
The first one, I think it's two.
Actually, over there. It's like the road.
No.
But it's still the same.
You do the same thing on the clock.
Yeah.
Yeah.
It's not life size.
Yeah.
This was a -2 on bottom.
Keep going, keep going.
Oh, I haven't even started, I've barely started this.
Did it.
Oh.
Yeah, 1/1 thing.
So just.
Yeah.
I got.
Yeah.
I did it the way that you just.
Oh, it's been talking.
Well, okay.
That's what I. You know.
Yeah, that goes.
I know, but it's.
That's part of the ground. Starting at -2. Going to 0. It's like that. Yeah, that's. Going down.
3 square, it's not.
Okay, so you see how
I got 1 - 9/1.
That's what I got.
Well, and then I got 4.
Did you flip them?
0 squared.
I mean, that's.
Yeah, and I actually wrote 1/4 and then I don't know why. But
Because you see how it says F, B, and A? So technically this would be A and this would be B. So then the 3 would be on this.
Yeah.
Because you see how it says B and A? So and there's more interval, so like those 2 would be A and 0 would be B. So when you set it up, 0 would be the first one.
I think I got the 4.
That's why I got 2, yeah, that's why I got 2 now. Because you don't wanna, because like, if you think about it, if you were to do it the normal way, with number 3.
Yeah.
1 puts out 3.
Let's see, so. Yeah. So. So instead of.
Yeah, it's, yes. Oh, okay. I'm good. I was scared that I took it as the.
Okay, guys, you can check your work up here. 3, 1. 3, 9, 1, and hopefully you'll get 4.
Yeah.
Yeah. It's okay if you're not done. All right, so hopefully these are, but for the ones that you have been able to do, you're getting these average rate values. Okay. Now, we know what the graph of x squared looks like, but let's pretend we don't know, right? We don't know what the graph of it looks like. If all I have is this average rate, from the x value -2 to 0, what's the graph looking like there? What should be happening to the y values? On average, they're decreasing. It could go up a little bit, but on average, it could be decreasing. So that's the whole point, that's on average. From the x value 0 to the x value 1, what's happening to the y values? On average, they're going to increase by 1 unit. And then from 1 to 3,
Increasing by 4.
on 4. So where is it going to be? Let's say you're a little person walking on the graph of f. Where is it going to be harder to hike up on the graph? Where is it steeper, I guess, the graph? On this interval or on this interval?
The third one.
The third one, because on average, the y values are changing faster than on this interval. And that's the kind of stuff you guys are going to be thinking about when you get to calc, okay? Okay. You guys ever watch the show Hot Ones on YouTube?
Yeah.
It's a really fun show where they interview celebrities and they give them like 6 or 7 really spicy wings. And each wing just gets hotter and hotter and hotter to the point where it's like really, really hot and they're like almost drugged up. And then they just basically say, you ask them questions and they'll just say whatever, right? Because they're all like spiced up. Okay, so let's pretend we're on Hot Ones. Here's a wing, here's another wing, and now I'm going to give you a spicier wing. Okay, so we're going to get a spicier wing. So you're doing well. Good job. Now the algebra is going to get spicy, okay? Gonna get nasty. All right, this is what's called, what the thing related to this is what's usually called the difference quotient. The difference quotient has to do with this stuff. So something you'll be studying in calculus is the average rate of change from x equaling a. I'm recording, right? Yeah. From x equaling a, no, from some x equal a, so from some x value a to any other x value x on the interval, and then I'll stop and explain what the hell I'm saying. From the interval a to x. So basically, your starting point stays at a. It would stay at whatever number it is. But this ending point will vary. And you're going to find the average rate from that fixed x value to any varying x value. Okay? So if you want like a little picture, this is fixed. That one doesn't move. This x value will vary. This guy can vary, kind of like the way I was showing you guys on Desmos. That one can vary. This one stays there though, okay? But we can apply the same concept that we were doing here, because it's still finding the average rate of change. So to find that average rate of change, I'll still be doing what you guys just did, find the change in y over the change in x. But what's my ending x value on that interval? What's my b?
X.
X minus the starting x value, which is a. So it's the same thing. So then I do the y value, output it at x, minus the y value, output it at x. So that looks the same. The only thing is that you guys see how here you guys were plugging in numbers? On this one, you're not going to plug in a number. You're going to leave it as x. Okay? This right here is what's called the difference quotient. This is what we're gonna call the difference quotient. And let's look at an example so you guys see. We're gonna continue on this problem that you guys just did, but now we're gonna see what the hell I'm trying to say here. Example. This is the way WebAssign will write the homework. It'll say, find the general expression for the average rate of change. Sorry for all the writing. For the function, so for f of x equaling x squared within the interval 1 to x. So we're gonna fix our starting x value at 1, and we're gonna let the second x variable vary. So we're gonna do exactly what you guys just did, except that this ending value stays at x. So it's the same thing that you just did. Except that now I'm gonna end at x, so the b is the x now, so it's x minus 1 over f of x minus f of 1. Okay, let me stop there. There's a lot of writing in that. Okay, here's where it gets funky. See how this looks almost identical to what you did here? Okay, what did you do with that 3? You plugged it in, and that 3 you squared it, right? But because I'm plugging in an x, I'm gonna leave this as just x squared. I just literally write the function again. Minus, here I do plug in the 1, so that's gonna be 1 squared. And then I can't, this time I can't subtract this anymore because I have a variable there, right? So this just becomes x squared minus 1 over x minus 1. Okay? But here's where it's gonna get hard, not hard, but spicier, is you have to simplify it. You're gonna have to do all kinds of factoring on the homework and try to simplify this. Okay? You guys remember how to factor the top? It's a certain type of factoring called difference of squares. Difference of squares. What was that? What was the difference of squares? So difference of squares factoring. The little formula that you guys learned is a squared minus b squared. We'll factor into a plus b and a minus b. That's what it factors into. Because when you FOIL this out, when you distribute it, you get a times a squared, a times negative b is minus ab, but then a times positive b is positive ab. So that negative ab and that positive ab cancel out. And then you got b times negative b to give you the minus b squared. Okay. So you're going to apply that factoring method to your numerator. If I try to use this formula here to factor this, look at this before we did this here. What's like the a here? Is like the x, and what's the b? Is 1. So that means that this is going to factor into x plus 1, x minus 1. All over x minus 1. And then what happens?
Cross.
And then you get that joy, right? Ah, I don't know. I love that feeling. Sun out. Get out of here. This feels good. Sorry, I get passionate about that. Okay, but here, this part's kind of funky. Let's just kind of internalize the algebra. So you're being asked to find the general expression of the average rate of change within this interval. You do all this work and then you get this expression, x plus 1. What does that mean? Yeah, what is that doing? Right? So you guys see how here you found for this function, the same function, x squared, you found the average rate of change from 1 to 3? Here, what x value is being used here? It's 3, right? So notice that if you plug in x equaling 3, then you're really finding the average rate of change from 1 to 3, right? So plug in 3 here. What do we get if you plug in 3? 4, which is the average rate of change that you found. Okay, but what this does, the reason it says general, is because now I can find the average rate of change from 1 to any x value, as long as it's greater than 1. So what's the average rate of change from 1 to 2? You get that 2 and you plug it in here. Because that is always going to give you the average rate of change. In this case, yeah, it's 3. Because if I plug in x equaling 2, here, 2 plus 1 is 3. So if you plug in x equals 3, you get that the average rate of change is 3 plus 1, which is 4. I'm tying it back to this problem.
Oh.
Yeah, see how this is the average rate of change from 1 to 3 for this function?
Yeah.
Which is the same function. And so what this does though is that it finds the average rate of change from 1 to any x value. You just have to plug it in at the end. But if I plugged in 3, then that means that I would get the average rate of change being 4 from the interval 1 to 3. Question.
So this is what you use if you know you need several and like a quick amount of time.
Exactly. Yeah, if you need like a whole bunch of different intervals from a fixed x value to a varying x value, which you will in calculus, then this is it gives you like the general formula of the average rate of change for this interval. Cool? Kind of? Okay. Then it gets even spicier. Okay? Yeah, here I'm gonna leave this here. And I'm gonna have you guys try a couple after the next part. Sorry. That's Spanish for oopsie.
That is not Spanish.
Version of it. Okay.
Different dialect.
So in most calculus classes, you change this, you change this a bit, and instead consider the average rate of change from x being a, which is again that same a, to x equaling before I write the next part. Do you guys see how these x values are, there are certain unit value away from each other?
Yes.
Okay, so for example, if, and this one that we did, we had 1 to 3. How far apart are these two x values? How many units? 2, right? That, your textbook that distance, it's gonna call it h. That gap between those two. So these are 2 units away. Away from each other. Okay? So what this is gonna do is that it's gonna say from the x value a to the x value a plus that h. A plus that h. Okay? In this context, a is 1. And you can think of 3 as 1 plus 2, which is 3.
So each is difference in x.
Yeah. So h is the difference between those two x values, like the gap between them two. Okay? And so in this case, let's do this. In this case, here's a. The other x value is h units away. So what is that going to be? The x value? If this is a, this is going to be a plus h. That's what we're going to call the x value, the second x value now. Okay. So then if I use these, if instead of writing it a to x, I write it a to a plus h, then the average rate of change is going to be the ending x value, a plus h, minus the starting h value, the ending x value, a plus h, minus the starting x value, which is a. But how do I find the y value of this guy? What do I have to do? What do I do? What do I have to plug it in? I have to plug it into f, right, to get the y value. So it's f of a plus h, a told you, minus f of a. Okay. I know, I'm sorry. Here, can you combine like terms on the bottom? Well, notice that there's an a and there's a minus a. So you can actually combine the a and the negative a and they cancel each other off. And so now the bottom really becomes what? H, and the top stays f of a plus h minus f of a. Okay.
How President is this?
How what?
President?
Hella,
Okay.
like core. Yeah. The algebra looks very different, but they're saying the same story. X minus a is the difference between the x values, right? But h represents the difference between the x values, which is why that's h down here. Okay, question.
So are we learning like mainly the same topic today, just like different, simpler and more complicated ways to say the same thing?
We worked our way up to this guy. Because that's the one you use in calculus. Yeah, question.
On that one, the x subtract the one, they crossed out. Why on this one, the a plus h and a plus h is crossed out?
Well, right now, this is a general formula for any function. Right now, this one was true for only this specific function.
Okay.
Yeah, if I change this function,
Oh, you crossed
To
out
something
x,
else.
subtract one, I started off it out because it was different squares.
exactly, yeah. But like if this was like some other polynomial or some other kind of function, the algebra is very different. Yeah, so in calc, this function becomes a trig function, an exponential function, a log function, a polynomial function, a square root function. So you got to learn the algebra of all those functions to find that difference quotient. I'm sorry, guys, don't hate me. I'm just a messenger. I know you guys are. It's all good.
I thought you invented all of it.
Oh, shit. I know, right? 1,000 years or hundreds of years of work. Okay, so we're gonna answer this same question by using, instead of using this version of the difference quotient, we're gonna use this version of the difference quotient. And then we're done. Okay? I know you guys are tired. Okay, so we're gonna do the same thing. For example. So find the general expression. I'm gonna just put dot, 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 dot within, or for the function x squared within. But now I'm gonna say, I'm still starting at x equals 1. But now I'm gonna say to 1 plus h. Like that. So we're gonna kind of do the same thing. The change in y is over the change in x, but now I'm gonna use this version of the difference quotient.
And
Did it
this-
say one?
Let's
Oh,
say
one
one.
plus the H. I read it as one.
Oh, yeah. No, 1 plus h. So how far apart are these x values? The difference of those two, which is still just h, right? It'll always be h on the bottom. So it'll always be h. But now we gotta do the y value at the ending point minus the y value at the initial x value. All right, let's see where the algebra takes us. Let me slow down. This is where it gets funky. You guys remember last class that we had? I had you guys practice this stuff, and your homework did too, right? You guys were plugging in really weird stuff into function because it was leading up to this. Okay, I'm plugging in 1 plus h into this function because that's the one it gave me. The homework might give you a different function, so then you'll use that different function. Okay, it won't always be this one. So I'm going to plug 1 plus h, and what am I going to do to 1 plus h? Perfect. I'm going to square it. And then I'm going to plug in the 1 and also square it over h. And so in this problem, this one's different from this one. Because here I had a difference of squares, so I factored the difference of squares. But here, I can go ahead and FOIL this out. This means I'm doing 1 plus h times 1 plus h. Right? Help me out here. What would that be? It would be 1 squared, which is 1, plus 2h plus h squared. So when you FOIL that out, you get 1 plus 2h plus h squared. And then minus the 1 squared, which is just minus 1. Let me slow down. What can we do on the top? Yeah, that 1 and this minus 1 cancel out. So you end up with 2h plus h squared over h. Now I want to see if I can simplify it by factoring any question.
You can't just cross out and make it a bottom.
You can't just go like that. You can't just go like this. That would be, you kind of can, but you have to factor out an h. Yeah, so you can't do that. So I can't do that here because of this plus, this is considered, think of it like this.
So you can factor out the H.
But you can factor out the h, and then when I factor out the h, let me see. When I factor out the h on the top, I'm left with what inside? 2 plus h. But now because this h is factored, now you can cancel it out. And so then I'm left with 2 plus h. That's weird. Okay. What is that? What does this result mean? Actually, any algebra questions? Okay. So how do I use this result? What if I said, what is the average rate of change from 1 to 3 how many units away is 3 from 1? 2. So what's H in this case? From 1 to 3, what's that gap there? How far apart are they? They're 2. So if I want to use this to find the average rate of change, I would plug in the gap between these two X values, which is 2. What happens when you plug in the 2? What's the average rate of change? 4 again. So it's telling you the same story in a different way though. And that's the part that's going to be hard. What you guys need to study is like understanding how to use each one. Okay. Oh shit, we got time. Okay.
I'm still confused. How do you
Yeah.
use it?
So this is giving you the average rate of change. Let me erase this part. This is giving you the average rate of change from 1 to 1 plus H for this function. Right? It's giving you the average rate of change, like a general formula, right? So I want to find the average rate of change from 1 to 3. I need to figure out what that H value is. H represents like the distance between these two. So in this case, H would be 2. You plug that 2 in here. And then you get 2 plus 2, which is 4. So that means that 4 is the average rate of change from 1 to 3, which is what you guys already found earlier. But now I could change it up. I can say, what's the average rate of change? Let me go like this. What if I said, what's the average rate of change from 1 to 1.07? What's H? H is the distance between these two, which in this case is 0.07. So then you plug in that H here. And then you get 2 plus 0.07 to give you 2.07. So that is the average rate of change from 1 to 1.07 for this function. So that's how you would use it. But they all have to start at 1 for me to use this general expression. Okay? I felt like I had like something else here. Okay. So as this H starts to get closer and closer and closer to 1, right? So as this H starts to get closer and closer to 1, what am I trying to say here? Hold on. Let me see how I said it. I said it better on mine. Yeah. So as this H gets closer and closer to 1, that average rate of change starts to become the instantaneous rate of change at x equals 1. Kind of like the speedometer at 1 hour, it'll tell you the instantaneous velocity there, right? And so you're going to get a function for that. Okay, it's going to give you kind of like a general expression. Those general expressions, instead of giving you the average rate of change, they're going to give you the instantaneous rate of change. Okay, those functions will be called the derivatives of the function that you're analyzing. Okay, I think we're done. Let's stop there. Okay, we're too tired. Oh yeah, we'll keep it there. Good job, guys. Yeah, I'll stay if you guys have questions.